Ready.
Okay, so it's time to start. So
Okay.
welcome to the seminar today. And so today we are very happy to have Dennis Chen from Berkeley, and he's going to talk about deformation theory and coalgebras. So Dennis, please.
Okay, so I just want to give a brief outline. First of all, most of this work is joint with my good friend Herman Stefanic. And yeah, let me just start with a little bit of an outline of what's going to happen. First, I want to just recall some deformation theory. Just what does it mean? Deformation. We'll call some classic results. Okay, second, I'm going to talk a little bit about causal duality. Let me not abbreviate it, causal duality, and as well as bar-cobar duality. Cobar. This is the key thing that will link us from algebras to coalgebras. 3 is I want to talk briefly about coalgebras and the problem of rectification. And I will explain soon enough what rectification means. And then 4 is, the main thing of the talk, which is deformation theory using coalgebras. Okay. All right, so let's begin with some deformation theory. So classical deformation theory. So what is deformation theory? Well, it's a very general field of mathematics that attempts to classify sort of infinitesimal deformations of certain, various types of mathematical objects. So it tries to classify sort of infinitesimal deformations. Okay, and it basically, hope you've all taken calculus before, it tries to expand the techniques of differential calculus, taking derivatives, thinking about tangent spaces, and tries to take that, use those techniques to study like schemes, used to study like stacks, used to study manifolds, all sorts of things. So it tries to extend differential calculus to basically a more general situation, more general contexts. Okay, so let's start with an example. So something that we all have probably seen many times is if you're given a manifold M, it has what's called a tangent space, right? So given some point X in M, one can think that the infinitesimal deformations of this point are characterized by the tangent space of M at this point X. So this is a vector space. It somehow is the closest linear approximation to M, at that point. And yeah, I won't be speaking too much about this type of deformation theory because we are here to study algebraic geometry after all. So the second one is, let's talk about Kähler differentials, HLER differentials. Okay, so Kähler differential. So what is a Kähler differential? So given, so all my, okay, for now, let's say we're given a map from A to B of commutative rings. Okay, there is such an object called the omega, I guess, B over A. Sort of, you think of this as what is the like cotangent kind of exterior differentials kind of thing, and it satisfies this kind of universal property, which is that if I give a map of B modules, so this is a B module, it's a module over B. If I give a map of B modules from this to some B module M, it's the same as if I gave a commutative algebra map, sort of A on that has a map from, so, okay, let me back up. This is the category whose objects are things that lie between A and B. Yeah, things that have a map from A and it has a map to B, such that when you compose this, it gives you back your original guy F. So that's what I mean by this category. And this Helm space will be equivalent to this Helm space. So it's the same as mapping B into this sort of square zero extension of B. So this you should think of as the ring, who you have the objects of B, and then you formally adjoin the objects of M, but you make them square zero. So everything in M, you take two things in M, you multiply together, it's square zero. So this should be sort of a thing that you think of, when you think of like the dual numbers. It sort of has to do with tangent spaces, has to do with first order deformations. And yeah, one can clearly see, I can draw this in a better way, that, basically maps like this, I'm just going to rephrase what I did, are in one-to-one bijection with maps, I'm going to draw the A and the B above, that sort of lie between A and B like this. This has a projection to B again, and this is equality. These guys here are also known as alinear derivations from B to M. If you've seen these before, an alinear derivation is just a map from B to M that satisfies some sort of Leibniz rule. So, if I take the D of some B times B prime, it's going to satisfy a Leibniz rule relation, B times DB prime plus B prime times DB. And all of this has to do with calculus. You can see this calculus, this first order deformation thing. And this hopefully is something that rings a bell to some of y'all. Okay. So these are classical objects that people have studied, basically the roots of deformation theory. And let me remind you of a result that shows that like these Kähler differentials sort of classify first order deformations. Okay, so this example goes back to Kodaira and Spencer when they were working on complex varieties, but it's true for basically any any scheme over a field, I believe, that's well behaved enough. So let's say that we're given a nice, I'm just going to put nice there because the hypotheses really don't matter. Okay, a nice scheme X over a field K. Okay, you can actually, yeah, let's just make this a variety, whatever. What is a first order deformation? First, let me just introduce to you what a first deformation is. Let's think of X as lying over spec K, right? That's what it means to have a variety over K. It means it has like a natural structure mapped to spec K. Okay, now what I can do is I can take spec K and I can infinitesimally thicken this point to give myself the dual numbers. And if you don't know what the dual numbers is, it's just literally the free polynomial ring, but you make the variable square zero. So epsilon I write to mean a square zero element. Its square will be zero, just like this T here. So this is what the dual numbers are. So this object you should think of as a point, right? Just like that. This object you should think of as a point, but has this infinitesimal thickening. This D has a first derivative, sort of. It's slightly thicker than your regular point. And so we define a first order deformation of X to be some variety, some scheme, I guess now, some scheme X sub epsilon that fills this square. So now this square is commutative, and such that this is a pullback square. So this has to be a pullback square. In other words, X has to be the fiber product of these two. Okay, and this is just intuitively encoding the thing that, like, if I take, if I just pull back this variety along the point, this point inclusion, I should get back my original X. So it's just saying, I'm taking X and then I am thickening it. When I pull back, I shouldn't get something else, right? Okay. All right, so given such a setup, such a guy, So now I'm going to delve into a little bit of a more complicated algebraic geometry, but I hope you can still follow. Given such a guy, we always get a fiber sequence that looks like this. So try it. Let me give this guy a name, pi x, this guy a name pi x epsilon, I guess. Okay, so we'll always have such a fiber sequence. This is just a property of Kähler differentials, right? Every time you have like a fiber sequence or a push out of, sorry, not a push out, every time you have a pullback of schemes, you will always get some sort of sequence on Kähler differentials, and this is just that theorem applied to this pullback square. Okay, we'll get something that looks like this, relating the Kähler differentials of this guy with the Kähler differentials of this guy and this guy. This guy's Kählers and this guy's Kähler differentials with the Kähler differentials of the guy in the middle. This guy here. Okay, so we can pull this back to x. By tensoring it with O of x. Here, I think we just get O of x. In the middle, we get O of x tensor over this O of x epsilon, and we get O of x here. Okay, and now if you know anything about the X'd groups, this is just saying that this guy, basically given such a first order deformation, we can do this process and we will get an object of the first exterior group, the first X group, in this class. If you don't know what X'd is, you can just think of it as basically a group that classifies extensions that look like this, right? I have one guy here, I have another guy here. This is a group that classifies things that fit into this sort of short exact sequence. Okay, and this is isomorphic to, if you've seen sheaf cohomology, something that looks like this. Oh, sorry, I forgot some duals. I forgot to dualize a couple of things. I want to move this to the other side, I believe. Oh, excuse me.
It should be.
Yeah. I think I reversed. Is this what you mean? Okay, yes. I might have reversed things. Yeah, and I think this might have a shift or no shift. Okay, but something like this. Anyway, you can basically, if x is a smooth, you can sort of dualize this and get the tangent sheaf on this side, and you can move that to the other side. You can dualize things, and this will eventually be, at the end you'll get something that looks like the first cohomology of the tangent space of x. But anyway, this is where the Kähler differentials show up, and you can see it's already very useful for characterizing, or at least giving us a hint of how to think about these first order deformations, right? Given every first order deformation, we get a class inside of this group that has to do with these Kähler differentials. Okay. So let me just summarize this, as this gives us sort of a map from sort of first order deformations of x, which I write as x sub dual numbers, or def sub dual numbers of x, into this group. Okay. Cool. All right. Any questions so far? This might have gone a little fast, but okay. All right. So that was all more classical kind of style deformation theory. Later on, okay, let me just move to the next section. So this is 1.1. And I have to talk a little bit about DG techniques and infinity categories. So don't be too afraid. I will not go into the hard details, but this comes from historically, one point of view historically is that people eventually realize that the cotangent, the Kähler differentials, this guy, is well behaved when x is a smooth variety or a smooth scheme. So this goes back to Ilussi. And Ilussi kind of realized that when x is not smooth, kind of this thing doesn't work so well. And let me just list a couple of facts that work, that is true about these Kähler differentials only when X is smooth. So when X is smooth, we have a couple of things that are very nice. Let's see. So the first one is, okay, so given three smooth guys, whoops, we get an exact sequence, like a full exact sequence, like this. Where Z to over Y to 0, maybe with some pullbacks. I think I might have forgotten some pullback. Yeah, maybe this is F and this needs to be pulled back. Okay, but when X is not smooth, this part is not exact. Like this might not be injective. This may no longer be injective in general. But when X is smooth, or I think you only need one of these guys to be smooth. I don't quite remember which one. But when you do have like some smoothness hypothesis, you do get a full exact sequence, which is very, very useful. Second, and this is something that is more related to representation theory, but there's a famous HKR theorem, for example, which is, oh gosh, do I remember the three people's names? Okay, I'm gonna defer that for a second, but let me just say what this theorem says. It has to do with the Hochschild cohomology of X. So the Hochschild cohomology of X, one should think of as like functions on the loop space of X. And this is starting to get into like higher categorical things, but people consider things like loop groups. Like my advisor, David, he thinks about these things all the time. And the Hochschild cohomology is basically a way to study the loop group on X. This one should think of very vaguely as maps from S1 into X. You know, it has a natural S1 action. There's a lot of like interesting math to be studied here. And the Hochschild cohomology gives you like the functions, basically like the O of whatever, gives you the functions on this guy. This, when X is smooth, actually can be calculated very nicely as the symmetric algebra on the Kähler differentials shifted by 1. And these are both DG, right? Hochschild cochains is a sort of a DG construction. This is a DG algebra, which I'll get into what that means in a second. But basically, you should think of as this thing, which is like fairly difficult to compute, can now be computed in a very simple way. You just need to know what this cotangent complex is, and then it's some kind of free DG algebra generated by this guy. So understanding the cotangent complex really helps you out here. And third, I think this is only true when X is smooth. So if you think of deformation theory, like first order deformations, like I said above, when X is smooth, not only do you get a map like above, you get an equivalence. So deformations, first order deformations of X, in fact, are equivalent to this guy. So the map I had above will be an isomorphism in this case. And furthermore, not only do you have that, you have the automorphisms of these deformations is equivalent to H0. Okay, so these are all very, very nice theorems, but they only work when X is smooth. When X is not smooth, sort of all of these things fails. I guess like there's a level 0 one. Like this is a basic check, which we know for manifolds. We know that the dimension of X is equivalent to the O of X dimension of this guy. Right, that's basically saying the tangent space or the cotangent space, its dimension at a point should be the same as the dimension of your manifold. That's something that only happens when X is smooth. When X is not smooth, all of these can fail, unfortunately. So what do you do? How do you fix all of this stuff? We still want an object that looks like this, that satisfies all of these properties. However, yeah, basically, how do we solve that problem? And this is a common solution that I think happens a lot in geometry, which is if your X is not smooth, you resolve by smooth things. Okay, X is not smooth. There's no problem. Just resolve. Use some sort of resolution by smooth objects. And this is like a common sort of idea. And basically what Elusi and other mathematicians around this time did is they figured out how to calculate using a smooth resolution of X, like a variant of the cotangent, this cotangent guy, the cotangent sheaf. See, yes, they described what something called the cotangent complex, which is usually denoted L sub X. And let me just say some words about how to calculate this thing. So the first basic fact of this thing is if X is smooth, then L of X agrees with the cotangent sheaf above. It's the same thing. Okay. Now, if X is not smooth, you have to do some resolution process. And let me let me try to go over how that works. So example. Let's see. Let's let X equal something very simple. So what is the easiest thing that I know is not smooth? Well, it's this spec of the dual numbers. It's like infinitesimally thickened point. It's definitely not smooth. Okay, so let's just think about what happens when I just take this, right? This, I think what happens is you get, let me see what happens. Yeah, I believe what you get is you get just a k in degree 0. Something that looks like this. It's just k, I believe. No. It's not just k. Is it? No. I think it's one dimensional. Okay, it's something like this. We will see what it is. I'll do another calculation that will tell us exactly what it is. But anyway, this already fails the level 0 thing, which is that this has dimension 1, whereas X as a scheme has dimension 0, right? It's an infinitesimally thickened point, but it's still a point. It shouldn't have any dimension. Okay, so now I'm going to tell you how to calculate L of X. So here we need what are called DG algebras, differential graded algebras. These things are basically just an algebra in chain complexes of, of vector spaces. So you probably have seen chain complexes before if you've studied homology or cohomology of topological spaces or sheaf cohomology. It's the same thing. What are algebras over this thing? Well, this thing has what's called a monoidal product. It has a tensor product, and you can literally write down the same axioms as you do, like for in basically any setting. If you know what an algebra inside of vector spaces is, you can write down the axioms being like, okay, what is an algebra? Well, I have to have some multiplication, right? And then I have to have some associative law, something has to commute to be a tensor V. Okay, you can write down all of the same thing in chain complexes. That's what a DG algebra is. Okay, so how do we resolve this guy? We need to find something that is smooth that resolves this guy. So one of the basic techniques in using DG algebras is, instead of imposing this relation t squared, we're going to think more homotopically. We're going to say, I want t squared to be 0, but I'm not going to force it using an equality. I'm going to force it using something in the H1, something that's like a one-dimensional cell that tells me that it's 0. For those of you who think topologically, this is literally adding in like a 1 cell, adding something in like in degree 1. So let me write down exactly what happens. We're going to start with k adjoint t. Okay, we're going to add a new dude in degree 1. This is sort of thinking as a 1 cell. And what we want is we want d of this epsilon, d of this eta. So we want d of eta to basically be this thing that tells me that t squared should be 0, right? This you think of as the really something that's saying t squared minus 0. It's identifying these two things. This you should think of as, if I have 2 points, right, in a topological space, how do I add a cell to identify these two? Well, I add an edge, right? I add an edge whose boundary are these 2 points. This is exactly the same thing. I'm adding a new guy. I'm adding an eta whose boundary is t squared and 0. And this is a chain complex, right? I literally tell you what d of eta should be. This is my degree 1 elements. They're all things that look like t, k adjoin t times eta. Those are the only things in degree 1. These are the things in degree 0. It's just my k adjoin t guys. What are the things in degree 2? Well, luckily for us, a DG commutative algebra, everything in degree 1 will have square 0 automatically. That's just part of the axioms, or that's just part of what happens when you write down those relations. So in fact, we'll have nothing in higher degrees. Okay. So this is a DG algebra. This thing that I guess I'll call this T, which is in degree 0. So that's one generator. We have another generator in degree 1 that witnesses the fact that t squared and 0 should be identified. And we have some, something that says, what should d of eta should be? Well, it should be equal to t squared. Okay. Now, the benefit of using this format is this is what is called, it's basically something that's well behaved for you to take cotangent complexes. It's what's called quasi-free. It's like it's basically a free DG algebra, except for this differential guy. Like if you just forget differentials, it is a free graded algebra. It's free. It's literally k adjoin t and epsilon. So these are the kind of the smooth guys in this context. So now let's take the Kähler differentials. We can now take Kähler differentials, and we're going to use that rule, basically this rule, that if x is smooth, or in this case, I guess I mean well behaved enough, that the Lx and the Kähler differentials agree. So instead of calculating Lx of this guy, well, Lx of this guy, what I can do is I can resolve it using this dude. This is a resolution now, and then I just calculate the Kähler differentials of this guy. Let's see
when you say free. When you say free is over kt, or over which?
It's just free over k. Yeah.
Free over k.
Yeah, it's a polynomial ring in 2 variables, so it is free.
Yeah, so it's free more than just quasi-free.
Yeah, it's quasi-free because if you ask for what are things that are strictly free over k in this category, I think you all have to have very trivial differential. It turns out that having non-trivial differentials is okay as long as if you forget the differential is still free. Like quasi-free is good enough, it turns out. This gets into homological algebra kind of stuff.
Mm-hmm.
Okay, cool. So now let's calculate this guy. And how do we calculate this guy? Well, we calculate exactly how we calculate the cotangent complex of something that is free. We will get something that looks like this. D eta plus, this is exactly how you calculate k adjoin xy, right? Its Kähler differentials will look something like this. You'll have the k adjoin xy dx, k adjoin xy dy. Those are the two things you get. Here, this is kind of in degree 1. This is in degree 0. This is not really in degree 0 because I guess you can multiply by eta, but let's ignore that because what we can do is we can take this guy and we can actually tensor it by k adjoin t divide t squared. And that's just because this guy right now is a DG module. It's a module over this ring. Okay, that ring it's a DG ring. Okay, you have to think about DG modules. Let's not do that. Let's use the natural map here that basically kills eta, right? Eta is now sent to 0. And if eta is sent to 0, t squared and 0 have to be identified because if eta is sent to 0, d eta also has to be sent to 0. So this forces t squared to be 0. So we're just tensoring this guy. So we're pushing forward from, this guy right now is in a mod of a DG ring, which is kind of difficult to understand. It turns out the techniques of homological algebra allows us to push forward this guy, so we don't have to think about that stuff. And what we get is we get a module that looks like this. Let me not draw the plus because it is a chain complex. dt, and we have a differential. How does this differential work? Well, what should the differential of D8? Oh, I should I have a D here. That's probably bad. Let me draw a different differential. Well, what should this be? We should just take the derivative of whatever this thing's mapped to. So what's the derivative of t squared? Well, it's 2t dt, right? So this del should take the d eta and send it to 2t dt. This one should think of as, if eta is equal to t squared, then d eta should equal to 2t, this kind of calculus-like equations. That's where this comes from. Okay, so this is the Kähler differentials of, not the Kähler, the cotangent complex of this guy. Now let's analyze what happens. Okay, notice that it looks sort of like two-dimensional, right? There are two guys here. That's kind of unfortunate. We kind of got further. We were one-dimensional here. We wanted to get to zero-dimensional. Oh, this guy's suddenly two-dimensional. Well, how we calculate the dimension of a DG algebra is actually by Euler characteristic. So if you've seen topological spaces before, you know how to take Euler characteristic. You take an alternating sum of the different degrees. So this guy is going to be plus. It gives us a dimension 1. This guy is going to be, it gives us a -1, actually. Sorry, I switched it. This one's a -1. This one's a +1. So this actually gives us this weighted sum dimension of 0. It remembers the fact that our original scheme was of dimension 0, which is really cool. And this is the guy that you would use to fulfill all of the desiderata, all of the things that you desired above. So all of these things, they don't work for the Kähler differentials, are in fact true for this cotangent complex, because you basically resolved by things on which the Kähler differential works well. So in fact, how you get these theorems for x not smooth, you just replace omega with this L guy. And hopefully this is some insight on how to actually compute these things. There are things called quasi-free resolutions. There are a lot of homological algebra techniques, but one can make these computations, which is cool. Okay. So the upshot, let me just rewrite the upshot. Is a lot of these classical things. So for many theorems to be true, so like classical theorems, a lot of the times when you see like this smoothness hypothesis, oh, I need this thing to be projective, or there's this and that, there is usually an infinity categorical concept that basically obviates the need for those hypotheses, but you need to work with a more enlightened object that removes sort of like these smoothness hypotheses, kind of things like that, but requires a more enlightened object. And what do I mean by more enlightened object? Well, I mean the object remembers more, right? This guy, we computed it from something that was quasi-free, and this quasi-free kind of like is a more homotopical invariant guy. Instead of imposing a relation t squared equals 0, what topologists have learned is better to always just add a cell. Let me add a cell that witnesses two things are equal. Like I will never force two things to be equal. I will always add another cell, add a path between those two things, right? And let me just give you a simple topological example of this thing. Let me say what happens when I try to collapse S0 2 points, right? I'm going to take the push out, which is basically imposing the relation that the 2 points should be equalized to each other. Okay, classically what I get is I just get the point. Boring. However, if you do it in a more enlightened way, in this sort of infinity categorical way, never should I ever say two things are like just squish them together. What I should instead do is I should add this equation. How do I add that equation? I add a cell. I add a cell that witnesses those two things are equal. Okay. How do I then also make them equal again? Right. I'm basically making them equal twice. And in the process of making them equal twice, I don't get the point. I get S1 out of it. So this is the homotopy push-out. This is the kind of thing that you need to sort of study. This is the kind of enlightened constructions I'm talking about. The L, this cotangent complex is in a similar vein. It's kind of taking a kind of homotopy version of the Kähler differentials. Okay, any questions? I hope the students are still following.
So what's the intuitive reason why we get something in the end which is not homotopic to the point? I mean, I agree with what you said about collapsing by attaching cells, but if usually you would get something homotopic, right?
Yeah, that's the thing. Push-outs, this construction of gluing things together is not a homotopy invariant. In fact, if you do, right, it's not a homotopy invariant. That's exactly the point. If you do this thing, I'm trying to think of an example now. Okay, I can't come up with an example on top of my head, but this homotopy pushouts was invented by topologists, in fact, to make these constructions homotopy invariant. This is like the very answer to your questions, basically. The homotopy pushouts and homotopy limits and all this infinity categorical stuff were invented to make these categorical constructions homotopy invariant. They originally are, in fact, very much not homotopy invariant.
I see. Yeah, thanks.
Okay. Yeah, so that is also one of the things that this framework solves, basically. Things that are not homotopy invariant, basically you need this more enlightened concept to make it. So, okay. And just so we're not all going insane, let me briefly just show you what kind of object these infinity categories are. So an infinity category, we see that we sort of remember more things. We have like higher dimensional cells, right? In a one category, what do we have? We have objects. So these zero dimensional guys, zero dimensional, let me write dim instead of, and then we have one dimensional guys, morphisms. And that's pretty much it. Anything that's two-dimensional, well, what can be two-dimensional? What can go between two arrows? It's just an equality. That's it. There's nothing. There's really nothing. And three-dimensional, okay, what can go between two equalities? Well, it's another equality. There's basically nothing. Everything else is trivial. However, now we know, hopefully we understand, that instead of doing this, basically truncating, killing everything above dimension 2, we should keep that information. So in an infinity category, we have these zero-dimensional objects. We have these one-dimensional morphisms. We have two-dimensional homotopies between morphisms, you should think. For those of you familiar with the category of topological spaces, you should think of these as a homotopy between two morphisms, right? I have two maps from X to Y. I can ask whether there's a homotopy that witnesses, I can translate X into Y, right? And then we have three-dimensional stuff that is like homotopies between two homotopies. That's okay. Four-dimensional stuff, fifth-dimensional. Okay, it gets pretty complicated. But it turns out that for a lot of contexts, you need all of this complication to get the thing that is truly homotopy invariant. So this is the kind of category that we are working with. And most categories that you know have an infinity category version, like the category vector spaces. Well, there's a guy called chain complexes on vector spaces, but you make the notion of equivalence quasi-isomorphism. So you really need to invert by quasi-isomorphisms to do anything DG. And this should intuitively be obvious, right? Like you have, for example, if you have two topological spaces, and they're simply connected, then by Whitehead's theorem, as long as they have as long as they're equivalent on homology, these two are weakly equivalent, right? So a lot of the times, constructions you only want them to work up to quasi-isomorphism, which is isomorphism of homology groups, induces isomorphism on homology groups. Okay, and the various other things. There are variants of this, which I will talk about later. Okay. Any questions so far? You do not need to know the details of an infinity category. Typically, just an intuitive understanding is enough to really work with them, but yeah, the details can get pretty hairy, unfortunately. Okay. Okay. Now let me go to the next part. So 2. Oh, I guess it's 1.2, which is formal moduli problems. So this is the heart of modern deformation theory. What a formal moduli problem is basically a way to encode like an infinitesimal deformation. And how do we encode this stuff? Well, we follow Grothendieck. Grothendieck came up with the brilliant idea, and people around his era. He used the idea of using a functor to encode geometric data. Okay, what does this mean? Well, give me a geometric object X, right? Instead of considering X, I can consider how to map things into X. I can consider this functor instead. And if any of you have seen basic category theory, you know that this functor, in a way, knows everything that there is to know about X. This is called the Yoneda lemma. And Grothendieck also was thinking about how to define schemes via functorial geometry. You can do that in a certain way. By thinking of a scheme, you can sort of define it as, and this is a very rough definition, as a certain well-behaved functor from ring into sets. Okay, and why ring? It's because basically you should know how to map into a scheme using affine schemes. And what is affine schemes? Well, it's just the same as a category of rings. So basically this is saying that given such a scheme, it should be a functor. I should be able to basically ask how to map into it using a spec R. Yeah, it's basically telling me if I probe it using this affine ring, it's going to tell me the answer. Okay, what are the ways I can map into this X? And Grothendieck has really developed, and people following him developed this to a very, very high level. We're not going to use all of that stuff. We're just going to use, now I think I'm just going to define a formal moduli problem. But really in the same vein, we're going to use this kind of functorial point of view. Okay. So we're going to, instead of using all rings, we're going to use Artinian rings, Artinian augmented rings, Artinian ring augmented. Okay, so what is an Artinian ring? You should think of as it's something that looks like the dual numbers. It's sort of a ring whose geometry is like a point, and then various ways to infinitesimally thicken the point. So the dual numbers is one, k join t divided by any t to the n is an Artinian ring. It's usually defined as some sort of like finite dimensional ring or something over k. The augmented just means that there is an augmentation map to k. So there's always an inclusion of a unit, right? K includes as the unit inside of a ring. This is asking for a retraction to that. And all that this means is that this guy's underlying scheme is going to just be a point, right? Usually in Artinian rings, the underlying scheme can be many points, a finite number of them, but many points. Okay, so we add this augmentation, so we only pick out one point. And these you should think of as encoding deformation theory, right? We have the point in there, and then we have various wavy neighborhoods of the point. So this is the category that we will start with. So a functor, a formal moduli problem will then be defined as, so a formal, and I'm going to write FMP. Yeah, writing all of this every time is going to be very annoying. And FMPX is a functor from Artinian ring. So I'm going to immediately jump to the infinity categorical notion, but if you are uncomfortable, you should think of the one categorical concept. It's something that sort of maps this into sets. And I guess the infinity categorical would be DG Artinian rings. But there is a classical analog. So this would be a classical FMP. This would be a more enlightened infinity categorical FMP. This is the default of what I'll be working with. But once again, if you're uncomfortable, you can think of the classical notion for now. Okay, satisfying two major axioms, one of which is saying that x of a point, so how do you map into it using a point? Well, there should be no deformations of a point, right? Points should give you trivial deformations. You literally have no room to wiggle in spec K. Spec K has basically no infinitesimal room for you to wiggle around. Okay, and B is some sort of obstruction theoretic result. So, and this is the axiom that has to change in the classical way, which is why I prefer the more enlightened version. But let me just write out, if this is surjective on pi 0, okay, then if we have a pullback that looks like this in DG Artinian rings, then X will preserve this pullback. This will also be a pullback. Okay, now this this might look very arbitrary. What the hell is going on? Let me give you a very particular example that should tell you, enlighten where the obstruction theory is coming from. So if this is a pullback inside of DG Artinian rings. Classically, you don't have like such pullbacks. Classically, you have to do something weird, considering ideals inside of the ring, blah, 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 blah. This is another advantage of using infinity categorical notions. You can there are more constructions you can do, basically. But this is a pullback inside of this guy. This is t squared over t cubed. Okay, so this over here, oopsies. This over here is sort of degree 2 deformations, right? It's t divided by t cubed. This is t divided by t squared. So there exists a classical theory of thinking of first order deformations and asking, when is it okay for me to extend it to a second order deformation? And it goes on, when can I take a second order deformation, extend it to a third order deformation, blah, 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 blah. You can continue going on. And this is a pullback in DG Artinian rings. This, what the heck is this guy? This is the ideal. This is this as a module, right? This is an ideal. Literally the ideal that you need to quotient. This is t squared over t cubed. This is the ideal that you need to get this quotient. And I'm just considering it as a ring by making the multiplication in this square 0, by everything squares to 0. In fact, it does square to 0, even if you consider it as a sub guy inside of there, everything squares to 0. That's just what this is. Okay, so any sort of, there are many different diagrams that you can draw like this. A lot of the times when you have like a square 0 ideal, if this is square 0 inside of A to B, you will get a pullback that looks like this. A goes to B, goes to I, but you have to shift it by 1, goes to K. You will get such a pullback. Okay, so X of this thing should be a pullback. Now, what does that say, right? So what's down here in this corner is going to be your first order deformations. Okay, what's over here is something that has to do with oh, I forgot what goes over here. I think it has something to do with the tangent space of X. Yeah, this has to do with the tangent space of X, which we'll talk about in a second. This is just 0 because X applied to the K is just a point. I should draw a point here then. And this is third order deformations. So yeah, I'm going to talk about what happens when you apply X to guys that look like this square 0 things. This has to do with the tangent space of X. But essentially it's saying that I can know when to extend a second order deformation to a third order deformation. What do I need? Well, I need that the obstruction class to the tangent space goes to 0. Right? This is encoding this obstruction theoretic thing that's saying, if I have a class in here, how do I extend it to a third order? I need this class in tx shifted by 1 to be 0. So I think this has to do with the map above when we had deformation K, the Kodair-Spencer map, we had a map from here to x1 of Tx. It's saying that this map has to go to 0 is when it extends to a square 0, third order extension, I believe. So it's a little fuzzy how these connect classically, but it has a classical thing, obstruction theoretic interpretation. Okay, and this exists for all of the higher order deformations. Like you can extend an n order deformation to n+1 deformation using a similar pullback square. All right, so yeah, so these are our two axioms. One is just saying that, okay, X has to be a point. Second is basically some obstruction theoretic thing, obstruct. Any questions? Oh. How much time do I have? Could I ask?
Maybe only still 7 minutes.
Oh, I only have 7 minutes. Okay. Oh gosh. I think I might have gone too slow. Okay, let me see. So I defined an FMP. Okay. I'm stuck. All right, so I have to skip some of the examples I want to go through, unfortunately. Okay, the thing I mentioned before is that when you take an FMP, okay, you can apply it on these square 0 guys, K adjoin. Basically, okay, let me just write it like this. You can apply it to the dual numbers. This is defined to be the tangent space of an FMP. Right, this is sort of how you define a tangent space for a scheme as well. You apply it on the dual numbers, and that's the tangent space of a scheme at that point. It has to do with the Kähler differentials. They're kind of all interlinked, especially when the scheme is smooth. Here, when we're in DG land, we can actually adjoin this square 0 dude, this epsilon, in any positive degree or any negative degree, in fact, but we're going to consider just positive homological degree for now. These things piece together to something called to another DG thing. Okay. This is called I guess the DG. This is classical, right? This is only degree 0. This is now a DG thing if you look at all these higher degrees. And a key theorem that doesn't work classically is that FMPs over K are equivalent to DG Lie algebras, basically. And the map is by the tangent space. So X, if you take its tangent space, I think there might be a shift somewhere here or there. There might be a shift. I don't quite remember, but this has the structure of a DG Lie algebra. It comes from the usual structure on a tangent space that you think of. There's some like bracket of vector spaces, bracket of tangent vectors. And this is just encoding the very natural notion that an FMP should be determined by its tangent information, right? An FMP, all it is just you can only map into it by infinitesimally small points. That's all that this thing has. So it should be characterized by its tangent space. It's not quite, but it's characterized by its tangent space plus some Lie algebra structure on it. Okay, I feel like I do need to give an example of an FMP. Given any scheme, right? Given any scheme or affine scheme, actually any scheme works. Given any scheme, Y, there is an FMP that's called, and a point. You have to pick a point as well. There's an FMP called the deformations of Y at that point, which basically. It's going to be the functor that you can take in a spec of an Artinian algebra, map it to Y, and what you need that when you go into spec K, so let's call this Artinian algebra A, Y. When you pull back to spec K, you get this original point back. Okay, so any scheme, pick a point. You can ask what are the infinitesimal deformations at that point. And this theorem is basically saying that the FMP characterized by that should be given by, once again, the tangent space of that point. Maybe some sort of enlightened tangent space, but some tangent space nonetheless. Okay, and this theorem is by Lurie and Pridham. Okay, so in their proof of this theorem, they rely on something called causal duality. See, I am running very behind. So basically, causal duality is a way, let me just draw a diagram, and perhaps it will explain better than I can. So let's talk about commutative augmented rings. They have a cotangent complex, L, right? So what I was talking about, sort of, you can think of Taylor differentials if you're uncomfortable, but I'm going to think of the cotangent complex. And this is adjoint to the trivial functor, which takes a module and just gives you the augmented algebra that looks like M just has square zero multiplication. Okay, now what causal duality does, or Cobar duality, is saying that using some abstract nonsense, you can look at this comonad and ask what is the coalgebraic data of the thing that I get when I land in modules. And by comonadicity, you will get something here that looks like DG Lie coalgebras. And this will universally lift to an adjunction here. So this guy is basically what happens when you analyze this adjunction, and you'll always get a universal thing, a universal extra data that it will have. Sometimes it'll just be mod K again. Okay, then you're unlucky. But in this case, you're not unlucky because you get a natural DG Lie algebra coalgebra structure on your cotangent spaces. And then you dualize this, and when you dualize this, you get exactly what you get back above, which is this key theorem getting you back into DG Lie algebras, right? So you first get this coalgebra, and then you dualize to get the algebra. Yeah, so that is kind of where our research is trying to ask, is basically we have this great theorem that characterizes FMPs using algebraic data, but it jumps past this coalgebraic data. Is there a way to characterize FMPs using this coalgebraic data instead without having to dualize? And that kind of thing. So I'm jumping through my notes a little bit, unfortunately, but this kind of question led us to consider a lot of things about coalgebras. One thing in particular that was in our way was the fact that coalgebras do not rectify. So let me just briefly say, with algebras, we have a very nice theorem saying that the DG notion, right? If I have some sort of DG notion of algebra and I invert by quasi-isomorphisms, this is the same as if you go into Lurie's higher algebra and you look at his version of infinity categorical algebras, whatever, it's the same. They gave you the same answer, okay? Here, I never talked about infinity categorical algebras, but there's a way to define them. One can, if you are interested, look at, for example, things called operads by Peter May. He invented a version of E1 operad, which basically gives you associative things, E2, E3. These are ways that you can encode a homotopy coherent notion of an algebra. You know, basically the rules, the associative laws, the commutative laws, they don't hold up to strict equality. Instead, there's a higher cell, you know, that witnesses the fact that some things is associative, some things are commutative. That kind of idea. Okay, so there is a rectification of algebras. And one thing that Hermann and I ran into is the fact that for coalgebras, there is no rectification. So there is no such rectification law, which is very unfortunate because that means we can't use all of our favorite DG techniques. Hold on, let me go. Okay, and this kind of problem was studied before by Perot, I believe, and Soleil has some work on it. They also proved that rectification doesn't work, but their notion of coalgebra is a little different from ours. So we had to reanalyze the situation. What we were able to do, though, is for, let me just state it like this, for co-commutative and co-associative coalgebras, they're just commutative and associative coalgebras, the dual to algebras. If they're co-connective, so we were able to prove such a thing. Co-connective coalgebras, if you look at their DG notion, is equivalent to co-connective coalgebras in their homotopy coherent notion. And we were also able to prove, well, we were able to kind of disprove that there's no rectification for if you remove the this hypothesis. In fact, it's already not true for say commutative algebras. What is its dual? Its dual is that these DG Lie coalgebras. It's already not true for DG Lie coalgebras. They cannot be rectified. That comes from a statement. It comes from a remark from Lurie by Gates, which was recorded in Gates-Guerry-Rosenblum. They thought a certain functor was fully faithful. Lurie gave a counterexample. That same counterexample can be used to show that rectification can't happen here. And I'm happy to go into the details if you want, but I wanted to speak a little bit about this argument because I think it is quite nice. I'm seeing I don't have any time left. Yeah, let me just quickly say the argument. So these guys, there is always a co-radical filtration for algebras and coalgebras, right? If you have an augmented algebra, there's a thing called the radical filtration, which is the filtration by you divide by the maximal ideal to some power, right? The more times you have to multiply the maximal ideal, the closer you get to A. The less times you multiply the maximal ideal, the farther you get to A, right? There's this sequence. It approaches A as you have higher and higher powers of N. Similarly, there's a co-radical filtration. So coalg has a co-radical filtration. Unlike with algebras, this co-radical filtration actually converges. So for algebras, this is not true. It does not converge necessarily. It only converges for what are called completed algebras. But for our notion of coalgebras, it converges, which is very nice. That means that we can reduce this theorem to a theorem on these like truncated, co-radically truncated coalgebras. Okay, co-connective coalgebras also have another filtration. It has a filtration by cohomological degree. If you've seen like a Postnikov tower of topological spaces, that's another, basically the same kind of truncation by degree that we're talking about. So this also has a cohomological truncation. So using these two filtrations, both of which are convergent, we're able to reduce this case to the case of basically doubly truncated coalgebras, right? So they're truncated in both ways. I guess I'll write it. Maybe one of these is a co-radical, one of these is cohomological truncations. We're able to reduce this theorem to like this doubly truncated case. Now in this doubly truncated case, we are able to basically use the rectification of algebras, right? So we know that when things are suitably finite, when you take this dualizing functor, things work out. If things are too big, too infinite, not truncated, dualizing functor is no longer isomorphism. So in this context, we were able to then use the rectification of algebras with an enormous, enormous asterisk, because if you just dualize as is, you get from coalgebras, coalgebras over mod k modules to algebras over mod k op, the opposite of k modules, and mod k op is not a well-behaved enough category for rectification to be for the current theorems of rectification to work. So we had some extra work. We had to compare these with what happens when we end complete mod k op. Okay, now it is a well-behaved enough category for rectification in algebras. Okay, but then we have to basically see how those two categories compare, and things do work out. But yeah, that's how we proved rectification of algebras. And I unfortunately don't have any time to talk about coalgebraic MMPs. But yeah, thank you. Sorry for going a little bit over. Any questions?
Yeah. Any questions?
We have something similar emoji. Do we have something similar for D module of the field replaced by ring?
Oh, very interesting. E-modules. I'm not so familiar with D modules, but it's a very, very interesting question. D modules.
What about?
There probably still is some sort of Postnikov like filtration. But yeah, I don't. Yeah, I'm not an expert on that kind of thing.
What about replace field by ring, commutative ring? What about that?
What about? Sorry, what was the first word you said?
Now everything is over field K.
Oh, okay, okay. What about not?
Replace K by ring. What about that?
Okay, okay. Yeah, so if you replace K by a ring, some things go a little bit hairy when you consider commutative things. And that's because when you consider commutative things, like how do we talk about a homotopy coherent commutative ring, you're thinking of the functor that looks like this, right? So what is the free commutative ring on a guy? It looks like this. It looks like some sort of giant sum, and then you have lists of guys in V, and then you have this symmetric action. So this symmetric action kind of screws a little bit of things up, especially with DG. DG techniques actually don't work so well in commutative rings. So Herman and I are working on something that work in characteristic P, hopefully, but we don't have anything yet. It really has to do with the symmetric group action. It's a little bit difficult to work around. So not yet, but hopefully it's sort of in progress. So yeah, so our work unfortunately relies on characteristic 0. Hopefully later on there's some characteristic P thing and maybe even arbitrary rings once we get to it. Thank you for the question.
So the result is also only over characteristic 0, right?
Yes, Lurie's original result is also only for characteristic 0. Yeah, there is a different result for, I think, characteristic P, but you cannot use DG Lie algebras. You have to use what are called partition Lie algebras. But I think if you do that, it's okay. So FMP over K of characteristic P, I think are equivalent to these things called partition. And I think if you reduce a partition Lie algebra into characteristic 0, you get back just a Lie algebra. I think it doesn't. Yeah, I think it should recover everything. Thank you for the comment.
Also, in your talk, what are the statements that you have proven?
So we were able to prove. So the only one that I got to was this one. We were able to prove actually for any. Let me write it out in detail, so I feel like it's cool. So for any Q, co-connective co-operad. Co-connective just makes it so that you can talk about co-connective co-algebras easier. A co-operad is just something that sort of it gathers the notion of all the operations together, right? So like the commutative algebras, they have an operad called the commutative operad, which basically encodes all of the equations that you need for a commutative guy together. Co-operad is the same thing for co-algebras. Okay, so there's notions of co-connective co-operads. Yeah, we can define, co-connective guys. So what we really proved is we proved the DG version of co-connective coalgebras over Q. There's a natural comparison map to coalgebras, co-connective, using a more infinity categorical or homotopic coherent notion, and this is an equivalence. So we were able to prove for co-connective co-operads. In particular, what are some very standard ones? Well, co-associative co-operads, the co-associative co-operad, which I mentioned before, co-commutative co-operad, which I also mentioned before. Yeah, those things. Yeah, I wasn't able to get the. Yeah. Oh, please.
So for the last line, I guess your main result, what's the geometry in the background? What's the corresponding geometry?
What's the
So
corresponding?
for example, do we have any homotopy kind of theoretical meaning?
Yeah. So the homotopy theoretic meaning is interesting. It's basically the same kind of result for the rectification of algebras, and so let me talk about that. The rectification of algebras is a very interesting thing because it basically says, okay, let me not write the Q. I'm just going to consider, let's say, commutative algebras, whatever. It basically says, a priori, what we have is we have like strict, right? We have things that are algebras, I guess, on chain complexes. So here, I mean, we inverted by quasi-isomorphisms already. Here, let's say, down here is just algebras on chain complexes. And this, even if you take the homotopy coherent notion of this, guys, sorry, write that. This, since this is a one category, this just gives you just algebras again. Okay, so there's a natural comparison map from chain complexes to this infinity categorical guy, which induces a natural comparison map here between these guys. So we have a map from these chain complexes that are like very strict. These are literally just chain complexes on algebras on chain complexes with a tensor, right? And these are guys that are very messy. You know, to really encode this guy, you really need to talk about the EN operad or the E1 operad, I guess, here. So an algebra here is an algebra over the E1 operad. It's something that has all of these associators up to degree n, something very, very complicated. Here, you just have a strict multiplication, strict unit, strict everything. Basically, what this rectification theorem says is that any homotopy coherent guy, in fact, has a lift to a strict algebra that presents it, basically. So it's like a strictification result, which is why it's called rectification. Any homotopy coherent algebra with this weak equivalence notion of associative law, weak unit law, weak higher associative laws can be strictified. You can, like, you know, rectify it all, and you get something that's very much easier to compute with. And this is a similar kind of law. You know, it's saying that, once again, stuff that are homotopy coherent coalgebras, all these things, you can now use DG techniques. You can use DG techniques of like the quasi-free, you know, resolutions. You can use these things that I was talking about above. If this wasn't true, then yeah, that calculation I did above with the L wouldn't make as much sense. So it's mainly like a computational thing here. The thing that I want to get to later on is more geometric, but fortunately, didn't have enough time. Can talk about it in a sec, but yeah, hopefully that answers your question.
Can I just quickly ask about the answer? This homotopy upper script, is it taking DG nerf, or is it something else? What is it exactly? Homotopy upper script, like homotopyification, you said?
I just mean homotopy coherent, like algebras. I don't mean, so this is just a variant of algebras. When I write, I guess, algebras without anything, I just mean classical kind of algebra.
Right, but the process of homotopy.
Oh, how to do it.
Yeah, that's what I'm asking.
So there is a nice way to talk about algebras. The way that I usually think of it is just, you know, has to do with the E1 operad or EN operad, whatever. Here's a nice presentation if you have C with finite products. So if you have a C with finite products, there is a thing called a you can talk about simplicial objects inside of C, right? It's this guy. And I'm not going to go over too much what a simplicial object is. It's something that kind of looks like this. You have like A0, A1, A2, and you have morphisms that go like this. 2 maps here, 3 maps back, something like that looks like this, okay? So a way you can encode what an algebra is over C is you can just say, 1, I want A0 to be the point, okay? So there's one condition is A0 is the point. Second condition is what's called the Siegel condition. If I have AN, right, it's basically A, but I apply it to the n simplex, which is 0 less than 1 less than n, this should be a pullback. Let's say I pick a guy I, a less than 0. I can restrict to a less than 0 to I, and I can restrict to a for the guys greater than I, and these will converge at a single point. I want all of these to be pullbacks. Now this looks very wild. What the hell does this mean? Let me just draw the diagram of what happens now. So we have the point here, and we have no data, basically. This no longer gives me any data. Okay, we have one copy of A here. A2 will actually be A1 squared. Whatever A1 was, it'll be A1 squared. Whatever the 3 simplicities will be A1 cubed. The 4 simplicity will be A1 to the 4th, dot, 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 dot. The map back here will give me some multiplication, and then we'll have 2 unit laws here. There'll be 2 maps here, depending on whether I multiply the first 2 factors or the second 2 factors. And then there'll be 3 kind of unit laws. There'll be 3 maps here, multiplying the first 2, the second 2, the third 2 with the fourth 2, blah, 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 all of this data, right? So this is a way I can encode higher associativity. So something that satisfies these 2 laws is now a homotopy coherent algebra, something that like fits into such a diagram. This gives me the multiplication. These gives me the unit laws. Actually, this guy gives me a unit. Sorry, I think I drew this the wrong way. This should be exactly 1 map back, which gives me the unit. This gives me the unit in my algebra. This gives me the multiplication in my algebra. All this higher crap to the left is all of my higher associativity, higher whatever.
Mhm.
So this is one way you can encode an associative algebra, for example. There's a similar way you can encode a commutative algebra as well.
Okay, thanks.
Thank you very much. And are there any more questions? Okay, so if not, then Dennis again. Yeah, thank you very much.
Thank you. Oh.